So the last part of 3.1 is really the only part that has definitive problems attached to it, where you're actually doing multiple things. And that's how do we find the extrema, which means minimums and maximums, on a closed interval. So we had a theorem that said if an interval is closed, meaning the endpoints are included, and what you'll notice with that is they'll use brackets around the interval, or they'll actually use the word closed, which is nice. And if that interval is closed and continuous, there is at least one minimum and at least one maximum. I say at least because you could actually have a tie. You could have two places that are the highest or two places that are the lowest. So if you have a closed interval, it takes basically a four-step process, and the steps get easier as you go, to figure out where are these extrema? Where is this highest point? Where is this lowest point? So I'm going to actually go through the four steps while I do the first example with you, so you can kind of see how do the steps work in conjunction with an actual problem. So the first step is to find your critical values. And the reason that we call them critical values, for the word critical meaning important, is because those are the places where we potentially could have these extrema happen. I say potentially because it doesn't have to, but those critical values are going to be those options for where we're going to have the highest or lowest points. So we're going to take the derivative of the function, and it should be pretty easy to derive. Sometimes you can get kind of messy ones, but for the most part, they do a lot of power rules. One thing you'll notice in this chapter is we spent a lot of time doing some very difficult derivatives in chapter 2. We don't use as many of those difficult derivatives in chapter 3. They still show up, but they're not kind of the forefront, which is nice. Let's see. So we can factor out a 12x squared, so we get x minus 1. I didn't give you an interval. I need an interval here. Hold on, let me find my interval that I wanted to work with. Getting ready to say that you have to have a function, you have to have an interval, and I forgot to put the interval. The interval, obviously the interval is right here, -1 to 2. So I have two places that equal 0. So my critical values are x equals 0 and x equals 1. So the first thing you want to check is you want to make sure those critical values are even in the interval that you're looking at. You're basically taking like a snippet of this graph. And if you find critical values that are not part of that little snippet, that interval, toss them. We're not using them. So now what we need to do is we need to evaluate the function at the critical values. What I mean by that is plug them in, see what you get. I actually do these problems in a table format. You'll hear me refer to these as table problems. I just feel like it organizes things better. So I want to see what happens when I put 0 in and what happens when I put 1 in. And you're going to back to the original function. And you can use a calculator if you need to, although this one's pretty nice. You get 0 minus 0, so 0. And when you put 1 in, you get 3 minus 4, which is -1. When they don't let you use a calculator, you'll usually be working with very simple numbers. Well, then when you're on a closed interval, the highest point and the lowest point may not happen at the critical value. It may happen at the endpoints. And I'll show you what I mean by that. So let's say we're starting at A and ending at B. That highest value could be at the very beginning. That lowest value could be at the very end, or vice versa. Even when you have critical values, so let's say we go from A to B, you could have critical values in the middle, but it still may not end up being the highest point or the lowest point. And that's what we're looking for. We're looking for an extrema on this interval. So we also have to put the endpoints into our table. The more critical values, these tables can get bigger, but you're always at least checking the endpoints. So when I put -1 into the original equation, I get 3 minus 4 times -1. So I actually get 3 plus 4, which is 7. And when I put 2 into the original function, I get 3 times 2 to the 4th is 16. So 3 times 16 is 48. Minus, when I put 2 into the second one, I get 4 times 8 minus 32. Sometimes the arithmetic is harder than the calculus. I get 16. My last step really isn't much work. My last step is to actually just list what is the highest value, what is the lowest value. So right here, my highest y value is 16, so that is my maximum. My lowest y value is -1, so that is my minimum. Sometimes they'll ask for the full coordinate. If they just ask for the minimum or the maximum, you can just put the y value because that is how high or how low it goes. So let me show you another one. Take the derivative, so power out front, power 1 less. The 4's actually cancel. Minus the derivative of 2x squared is 4x. I can take an x out, which gives me x squared minus 4. And I can actually go further and do x plus 2x minus 2. So I get 3 critical values, 0, -2, and 2. Now look at your interval. And that's something that you definitely want to take the time to check. My interval goes from -1 to 4. That means that -2 is not even part of the graph that I'm looking at. So when I make my table, I'm not putting -2 into the table because I only want to know the highest or lowest in that stretch of the graph. So I'm going to make a table. Kind of running out of room a little bit here. I'm going to put in 0 and 2, my 2 critical values. I'm also going to put -1 and 4. So if you want to fill in the table all at once, you can. If you want to use a calculator all at once, you can do that too. So when I put 0 into the original function, I get 0. When I put 2 into the original function, I get, I get 16 divided by 4 is 4 minus 8, I get -4. Again, watch your arithmetic. When I put -1 in, I get 1/4 minus 2. 1/4 minus 2 is -7/4, or you can write it as a decimal, -1.75. And when I put 4 in, 4, that's going to be 64 minus 32. I'm going to get 32. And so then finally, my highest value is my maximum. Oh, didn't like me writing so close to the edge. And my lowest value is going to be my minimum. So again, those are called closed interval extrema. So I want to show you what they'll do on Delta Math, and that's going to be our last one in this video, because I wanted to make sure you were comfortable with the way they presented them. So this is what they're going to do. They're going to give you a function, and they're going to give you a closed interval, and they're going to ask either for the absolute minimum or the absolute maximum. So they're not going to ask both in one problem. I mean, you might get 3 minimums in a row. I think I might have set it up so you get one of each. I'm not sure. But you only need to put in one answer. So you still go through this process. So you're still going to take the derivative to get your critical values. So -3x squared plus 6x. I can pull out a -3x, which gives me x minus 2. So my critical values are 0 and 2, which both are in the interval. Again, you want to make sure you're not checking values that don't even end up in the interval, or else you could get a minimum or a maximum that's not what they were asking about. So I want to see what happens at 0. I want to see what happens at 2. I also want to see what happens at -2 and 4. So if I put 0 into the original function, I get -2. I'm going to pull a calculator close just so I don't mess up my arithmetic. If I put a 2 in, I get -8 plus 3 times 2 squared. So that'd be plus 12 minus 2. I get 2. When I put -2 in, I get a -8, -8. So I get positive 8 plus 12 again, minus 2. I get 18. And when I put 4 in, -4 to the third power is -64 plus 3 times 16 minus 2. I get -18. That is my absolute minimum, and that's the value that you're plugging in. It doesn't want the full coordinate. It looks like it wants the actual y value. So the lowest this graph gets over that interval is -18. So that is the last piece of the beginning of chapter 3. A lot of terminology, understanding extrema, understanding critical values, and how we look at different types of extrema, which we'll head into the rest of the chapter as we start to analyze curves.